I'm very happy to be here. And yeah, it's almost lunchtime. I can feel it. But right now, I'm really happy to talk about one of my favorite topics, actually, in AI, because it feels quite underrated, which is web AI. Right? So simply put, it's about running AI models in your browser using web technologies. And yeah, to start it off, I like to tell a story, because I always like to tell stories. So, I forgot, there will be a lot of AI-generated images in there, right? Just to say that, I'm not that good at drawing, so I do like to generate them. I use Nano Banana, just in case you're wondering, right? The more at the beginning, the less in the end. So if you say, oh God, this is too much slop, it gets better in the end, right? So yeah, the story. We're in the not-so-distant future, so maybe tomorrow. The world is obsessed with AI. Every day you get new headlines reporting about breakthroughs, for example, and talking of a better future together with AI models. But you also get other headlines, right? Some of them really fear-mongering, talking about the dangers, inducing fears of job loss. Interestingly, these headlines are often driven by the same companies, sometimes not too far apart, right? One week they tell you, like, oh, it's so great, you have this new model. The next week they tell you, oh, you know, AI could take your job. You should be careful. Maybe you give us more funding so we can make sure it's like safe and everything. But the problem is that these companies are mainly steered by a group of men, which we can call the tech bros. And while they do not agree on everything, right, they all seem to agree that AI is what can make them rich and what they can sell to the people very, very well. So they build big citadels, big, massive factories for the AI, filled to the top with servers and optimized for compute, nurturing bigger and bigger AI models, like this one. Models that sometimes seem to be alive, even though they are not at all. So models trained on so much data that it is actually impossible it was all obtained legally, but still they go on doing it and they build more and more of that. And they are selling the access to these models, setting their own limits, right? Like the maximum amount of tokens, today is this, like next week is this. You know, price per token, oh, sorry, we have to adapt it, we have to raise it. Usages per day, oh, you don't get many inferences anymore. And yeah, all while feeding them the customer data, actually, so our data, and creating bigger and bigger beasts, right? But there is hope, luckily. There are people that are working against these institutions, and I could feel it in the conference, right? It's quite good open source vibe here. And yeah, I mean, people from all over the world, basically, and are working on ways to make AI accessible and usable, and the resistance is real, right? We're many. We're scientists, students, practitioners, hobbyists, whatever. And even though we are all different, we are all kind of working together in a way to bring AI to everyone and to break them out of the citadels. And yeah, that's what I want to talk about today, getting the AI models out of the servers, out of the citadels of the big tech giants, onto our computers. Today, using web AI. We can do it in many ways. Today, it's about web AI. So, hello again. This is me, looking slightly tired there. I've got two small kids, so I'm often tired. Yes, and I'm Johannes. I'm currently the AI lead at a company called TechYard. We are situated in Germany, in Braunschweig, which everyone who is not from Germany probably does not know. But if you imagine like a map of Germany and you try to point in the middle and go a bit up, that's where Braunschweig is, right? Yeah, basically there. And we are mainly about consulting people for data and AI solutions, working with many small and medium-sized enterprises. So we see many problems, and we think of many solutions, right? And especially on-premise AI and getting stuff locally running is something that many people want, and that is still very challenging. So let's talk about our heist, right? The heist is, as I said, breaking the servers out of the Citadels. So that's the plan. Citadel, take the beast out, get it running on a laptop. Good. Why do we want to do that, right? So first of all, privacy, of course. Right now, every API call we make to the clouds, it's always sending data. We're sending our data. I mean, we try to think about what we send, right? Most people try to think of what they send. But sometimes, maybe you're getting, I don't know, sloppy. You send something like, oh God, I don't know, what happens with that data now? And I mean, the big hyperscalers, they tell us, okay, you've got this contract, this membership. Oh, it's okay, we don't use your data for this or that. But then someone like Sam Altman comes along and says like, hey, if you can't train on all the data, it's not fair. China will win, you know. Oh, China will win. And it's like, okay, so you can never really be sure about that. So if we can run stuff locally on our machine, it never needs to leave our systems, which is amazing. Then, of course, there's the lock-in problem. I mean, we see that in many companies now that they don't have just one product in AI, but they have multiple products. Like, I mean, Claude, I don't know how many things they have attached now to their Claude stuff. They're just trying to, you know, keep you locked in and not let you out. Then it's about availability. API calls can only be made if you have a connection to the internet. So that's good. And I guess most parts of the world are covered, oh, maybe not most parts, but many parts of the world are covered with internet these days. I mean, if you go with a train through Brandenburg to I don't know where, or Deutsche Bahn in general, people who drive Deutsche Bahn, they know the hardships of losing connections. And if you're in the middle of some, I don't know, brainstorming with some model and you're like, oh God, no, it's gone. I have to wait for, I don't know, half an hour sometimes. And then you can go on working, right? Not good. So if you can decouple the inference from the internet connection, that would be amazing. And then there's costs, of course. I mean, there are many charts showing that, okay, token prices are low, you know, it only makes sense when you have so and so many inferences, then you should run stuff locally or build up everything locally. And, well, I'd say that is true for bigger setups, when you need big servers to run stuff. But most of the times, even smaller setups are sufficient these days. And today, I will try to show you that even a laptop like mine, which is not really great, it's a Terra laptop. It's basically, I don't know, yeah, it's got an Intel CPU. It doesn't have a great GPU, just a built-in Intel GPU. We will talk about it later. And maybe I will also show something on my phone, which is a Fairphone 5. Also not that amazing, but okay, and we can run stuff on that. So the plan is, we have the model, we want to get it into our local machine. What do we need for that? Something it can live in, right? The habitat. So, okay, here's the habitat a bit bigger, because I like it. Because it's a nice thing. It took a while to prompt that, actually. But yeah. So let's begin building up the habitat, step by step. And we start with the bottom, basically the soil of it all, right? And the soil of our laptops is our hardware. So, as I mentioned, there's CPUs. Now, it's hard to tell you something new about CPUs, right? I mean, they exist. Since the times of, I don't know, John von Neumann and Konrad Zuse, who were like pioneers in that area. Of course, a lot has happened, but generally, we all know like there are some main architectures, the x86 and the ARM architectures. Usually they have few but very powerful cores, the CPUs, right? So few as in, I don't know where we are right now, 16, maybe 20. I think that's around the area most CPUs handle these days. And it's great for sequential processing. Of course, it can also do parallel processing up to an amount. And there are some big vendors like Intel, AMD, and ARM. But apart from CPUs, we also have GPUs, right? So the idea behind the architecture of GPUs is that there are not just a few powerful cores, but many simpler cores, which enables us to be highly parallel, right? And there's like this one here, single input, multi-threads. So that's like the motto of it, that we have one input and we can run this input on multiple threads at once, which is amazing to play video games, which I did most of my life with GPUs, but also amazing for scientific computing, right? And we all know, especially in the last years since ChatGPT, NVIDIA has become extremely rich by selling GPUs and building new GPUs and selling them for a lot of money. So yeah, that's GPUs. But then there's something that's a bit newer, and that is NPUs, right? So neural processing units. Neural processing units are a bit hard to grasp at this point because they come in many shapes. Most of them share the idea of systolic arrays. I hope I got the first thing right. I think it's systolic arrays. So the idea is that you have multiple smaller units called multiply and accumulate units that all basically work together, and then when you send data, it moves like a wave through these units. So they don't often write to memory, but they pass on the data directly to the next MAC unit. So this way they can save quite a lot of energy and are just way more efficient actually than GPUs. So they're not power efficient. They're probably not more powerful in terms of compute than GPUs most of the times, but they are just a lot more energy efficient, right? And I think one of the biggest vendors are most known for that is Apple these days. I guess everyone with a MacBook Pro has their NPU now, and I think it's quite a good bet. I also have an NPU in here from Intel. It's okay. Google has been in the game with TPUs for a longer time. Okay, so we've got CPUs, GPUs, NPUs. That's our soil, right? So now we have to build up on that with our tools. So which tools exist to run stuff in the browser? First of all, there's WebAssembly, because we know, when we want to write something when we want to run something in our browser, we need to write code. So natively, that's mostly JavaScript and TypeScript. That's not hard, right? You write it, you run it in the browser, it works. But the problem is JavaScript and TypeScript are not the fastest languages, right? You might have heavier workloads. I mean, in the talk before here about DuckDB, it was interesting because he mentioned WebAssembly a few times. WebAssembly or WASM in short. Because DuckDB, just for real efficient processing of, ETL stacks, whatever, you just need more speed than JavaScript and TypeScript can offer. So you need other languages. For example, Python, of course, very efficient. No. Stuff like C++ or Rust. Sometimes also Python. With that, you can create more efficient code because you get more to the near native runtime speed, actually. So WebAssembly is kind of the clue between that. So the idea is that we have our libraries. They're actually specific libraries for Python, for C++, whatever, that can create these WebAssembly binaries. So it's a compiling process where we create binaries that then can run in the browser through WebAssembly. The thing is, WebAssembly can only access really the CPU. It has no support for GPU or NPU. So to access these, we need something more. These days, there's something called WebGPU. But looking a bit back in history, there was something called WebGL that people might remember. Right? WebGL is, mainly built to render cool stuff in the browser, like a T-Rex. And then you can even, build a game with a T-Rex. run away from T-Rex or something. That works with WebGL, right? You can build nice browser games, 3D, you can render stuff, it looks nice, everything, but you can hardly run an LLM on WebGL alone, because it's quite constrained actually. So it's an old construct, and that is why WebGPU was introduced. WebGPU is basically the modern version of WebGL, you could say. And with that, you cannot just only render cool T-Rexes, we say T-Rexes, I don't know, dinosaurs. You can also do scientific computing, can run neural networks through WebGPU, because it is way more powerful through something called compute shaders and GPGPU. So GPGPU stands for General Purpose GPU, and I didn't make this up, it's a real thing. It's one of my favorite, I don't know, useless facts to drop at parties. Hey, do you know about GPGPU? It should only be at like nerdy parties, but yeah, it's something funny to say. Yeah, so if you ever need an icebreaker at nerdy parties, talk about GPGPU. Yeah, so WebGPU just makes it way more efficient to use all the architecture of the GPUs actually. And now we've got access to GPU. But what about NPUs, right? I talked about it, that it's quite a new thing. So we probably need something newer. That's where WebNN comes in. WebNN stands for Web Neural Network. So you already know where it's going. Okay, we want to run neural networks on the web. So the great thing is that WebNN is designed to run on everything. CPU, GPU, NPU, right? It's quite experimental, so it is supported in some browsers, but it's under development, and well, you can test it out. It's like an open beta thing, you could say, but it's not enabled on any hardware directly these days. But how do they do it, right? What's the idea behind it? So how do we get access to every hardware, basically? So the idea is to just use native runtimes by the vendors. So for example, you might know Core ML when you have a MacBook, right? Core ML is handling all the calls to like the CPU, GPU, NPU stuff when you do heavy computations. Windows ML is actually the follow-up to DirectML. I think it was DirectML. So that's the same thing for Windows. And then there's LiteRT, which is a bit of a different beast developed by Google, the follow-up to TensorFlow. What was called TensorFlow Lite, TF Lite, which is also handling like the processing or the communication to the underlying hardware, mainly for Android actually. So they mainly developed it to be able to run stuff on Android, and well, they also rolled out for other devices if you want, but mostly you need only the first two. Well, on Linux actually it also uses LiteRT. So yeah. The whole idea of WebNN is, okay, we don't write everything ourselves, like speaking to WebGPU, whatever, we just use what is there already. We use third-party tools, and then we talk through that. But make it available as a browser API, because WebGPU and WebNN are both browser APIs, right? So WebAssembly is compiling your stuff to a binary, WebGPU and WebNN is API you just speak to in the browser, and you can run stuff. Okay, now that we've got this, we need the frameworks. Because, we need something to load, to process, to, I don't know, just handle a lot of things around running models in our browser. And we have 3 popular frameworks. There are more frameworks. But here are, 3 of the most important at the moment, I would say. It's LiteRT again, right? It should be LiteRT.js here. You see it later. But it's a bit confusing. More on that in a second. So the first one is ONNX Runtime, right? It reads as ONNX. Most people say ONNX, like the Pokemon. I like that, so I will say ONNX. ONNX Runtime, first of all, needs an ONNX model. So the ONNX model format is kind of an interchange format, right? It's like we've got many different kind of formats. In the past, there were even more. Now we've mainly got like PyTorch, TensorFlow, JAX stuff, and you can all just convert it to an ONNX model, and the ONNX model can then directly be sent to ONNX Runtime, which is, for example, an ONNX Runtime web case in JavaScript library, which again can then speak to WASM, WebGPU, WebNN. Quite simple. Okay, that's all you need to know about ONNX Runtime, really. We could go into more detail, but I want to show you some demos in the end, so I'll try to rush a bit through that. Then there's Transformers.js, which I like, because I'm also a Hugging Face fellow, and I want to talk about Hugging Face stuff, right? So for Transformers.js, for example, you've got your app written in JavaScript, you import Transformers.js, then you get some cool functions like the pipelines, auto model, and auto tokenizer. So basically, it tries to mirror a bit the Transformers library you might know. You've got pipelines for like object detection. You can just call it like, okay, object detection, and it will fetch like a default model for you that can run. And yeah, it will fetch the models from the hub, the Hugging Face hub, and it should be in ONNX format because yeah, everything Transformers.js is working with ONNX. And yeah, there's also a tokenizer from Hugging Face that's a precompiled binary that comes with the Transformers.js and is also WASM format. Okay, then you basically, when you've loaded everything, you pass it to the core of Transformers.js where everything is done with processing, model config, batching, whatever you need. And then you pass it on to ONNX Runtime, which I talked about before shortly. And ONNX Runtime does all the handling and speaking to different APIs or WASM, runs it and WASM directly, whatever you need. So the idea is really just leverage ONNX Runtime because it exists and just do all the handling of the models before in the Transformers.js library. Now, LiteRT.js is building up on LiteRT itself, right? So LiteRT.js, the package, as I said, it's kind of a follow-up to TensorFlow Lite. So people know that people who know TensorFlow Lite, maybe TensorFlow Lite.js even, now it's called LiteRT.js because Google figured out nobody wants to use TensorFlow models anymore. So we need to open up and also support other formats like PyTorch, right? I mean, you can still use TensorFlow models, of course, but I think not many people do these days. And then they said, okay, let's just open up, but still convert everything to our TensorFlow Lite format. All right, so inside, when you've loaded the models, you still get TensorFlow Lite. And then it's basically just a LiteRT core that is compiled with WebAssembly that is then doing all the talking to everything else. And that's the whole idea of LiteRT.js. So yeah, it's an opened up TensorFlow Lite. Okay, let's talk about the models themselves, right? Because, I mean, we saw sometimes they're really big. LLMs in general are pretty big. Of course, there are also small language models these days. But yeah, we need to fit them inside our habitat somehow, right? So we need to shrink them. And again, a quick overview. I won't go into detail much on these methods. But these four are some of the most popular methods, right? Quantization. That means instead of using like the floating point 32 precision, we tune down the precision of the weights to something like, we could do floating point 16, which is just a bit of gain, but it's even better if you do it into integers like int 8 or even int 4, which also gives the benefit that MPUs are optimized for running on integers actually. So that's when we want to run it on an NPU in the end, it just makes sense to quantize it to some integer data type. And then there's pruning, which is basically just saying, okay, we've got this huge graph of our neural network, but we don't need everything of this, right? Because when we've done some inferences, we know, okay, maybe these branches, they're not that active, so we can cut that away and that away and that away. And in the end, we just get a real smaller graph of our network, which is still working pretty well and mostly doing what it's supposed to do. Distillation is the idea of having a teacher and a student. So there's a teacher, which is a bigger model usually that knows a lot, that can do a lot. And then there's a student model, which is usually a smaller model. And the teacher model is trying to kind of teach the small model to perform well on stuff. So it's trying to get the knowledge and the abilities of the bigger model into the smaller model by directly kind of interacting and monitoring between these two. And then there's graph optimizations, which is mostly done by ONNX Runtime, luckily. So we don't have to worry about that so much, because it just looks at the compute graphs of the neural networks and it tries to optimize these things where we can put stuff together or whatever. So it's doing a lot of that. Okay, now let's look at the full picture of the habitat, right? So we've got our model, which, for example, lives in the Hugging Face hub. Then we've got the frameworks, Transformers.js, for example, which is then interacting with ONNX Runtime and LiteRT. Then from there on, we branch it out to WebAssembly, WebGPU, and WebNN. WebNN itself is interacting with WindowsML, CoreML, and LiteRT. And then these are speaking to the hardware, CPU, GPU, MPUs, right? Great, so that's the full picture, basically, of everything I just talked about. Sounds solid, right? But of course, there are issues, because everyone would use it if there weren't any issues. Here are some of the biggest issues, right? So, download time, for a start. Many times I sat in front of this laptop waiting for a model to download. Because, I mean, to get models running on your local machine, you need to get them first. And when you have bigger LLMs, for example, I mean, even like 4 billion parameter LLMs are usually around, I don't know, 3 gigabytes, something like that. Depending on your connection, like the hotel connection yesterday evening was really bad, so I just stopped it halfway. But yeah, you just need to get this stuff. Once it's on your machine, it can be cached, of course, by the browser. Then it's really easy to start it up again, but the initial download time can be really long. And then you have to trust that the browser is not throwing it out of the cache under some memory pressure again, because we've got limited access to what the browser does with its cache, right? That's a problem. Then there's memory constraints. Before in the talk about DuckDB, it was mentioned that usually the browser gives you some constraints when you run your code in it. With WebAssembly, it's often around 4 gigabytes. I can't exactly tell you around WebGPU and WebNN, but there's just a big memory limit that comes from the browser directly, because it's a kind of a sandbox, right? It won't let you directly access other stuff. So it tries to constrain whatever you can do, and you have to kind of work against it. So that's a bit hard. Then there's a performance gap, of course, still. So between like stuff that you run locally or can run locally and stuff that can run in the cloud, it's still, there is a gap, right? Let's be honest. And then there's the intellectual property problem, right? Because so when you want to sell or when you develop a model, you're a company developing models, I don't know, fine-tuning models, and then you want to make money out of it somehow. Whenever you ship a model, you need to ship its weights in a way. So you can't really obfuscate the weights. There are some ways to like encrypt or whatever, but it's all like when there's someone really dedicated to get your weights, they will be able to get the weights when it runs locally, right? So the business models have to be sort of. Maybe that's like a secondary problem, but I had questions around that before in talk, so I was like, okay, I take it in. Another problem is the browser compatibility, right? So what runs where? And it's difficult. I mean, WebAssembly basically runs anywhere. It's been around for long enough. WebGPU, since last year, around November, December, most browsers are supported. So Chrome, Firefox, Safari, I think it's in a nightly or something. But so anything that runs a Chromium engine is quite fine. That's good. I mostly use Brave myself, so that's good. WebNN, as I said, is even more experimental. So it's behind flags on Chrome and also on Firefox. But everything apart from that, it gets difficult. yeah, you can look it up when you follow these links. It shows exactly where, like, the current status of the implementation. Okay, so these are some of the main issues we have around. Now, let's go to the fun part, some samples. So, I think I will start here. Oh, no, wait a second. Just do it like this. No? God. Give me a second. I might be able to figure it out. Huh? Maybe you can just F11 the whole thing. Yeah, let's try it like this, right? So that's like the official WebNN website, and they've got some demos on there. And yeah, down here are the older ones, up there are the newer ones. You can see that. So one of my favorite demos actually is this pose landmark detection with YOLO 26 and pose. All right, view demo. So what you see here is basically the demo. Here you can choose whether you want to run it with WebGPU, the WebNN GPU support, or the WebNN NPU support. And right now it's loading the model, right? Loading model. That's always the first step. And then it will use my camera to run a post estimation model. Ah, there it is. So I can't see it anymore. I'll just do this. Maybe you see my hands. Maybe I have to get up here. Get up here. Is it? Yeah. It's working, right? You also see a frame rate down there, like the 6, whatever. It's okay-ish. I can move around. It's not real time, but it works. And you can also look at my system. So when you look here, you can see it utilizes a GPU, right? The problem with this demo is the NPU stuff is broken somehow, because when I try to use NPU, it's not using actually the NPU. I can click on it, but then you see in the monitor, it's not using the NPU. So something is bad with that demo actually. Let me show you the monitor again. Oh, now it is using it, okay. Nothing is wrong with the demo, it's perfect. Right, so now you see the NPU is being used. So it's working, right? There's not a big efficiency gain, actually. Maybe you saw that as well. Maybe it gets a bit faster. I get up here again. Oh yeah, okay, it's around 10, 9. So it's better than the WebGPU implementation, which is good. But you don't see, oh, now you see it. Yeah, it's a bit different like from this, what it detects, actually. Now it detected, yeah. Great. Okay, there are actually a lot of computer vision demos. So when you're on the website, you see that. Yeah, going back is hard. Come on. Or not. F11, no. Going back. Yeah, there are actually quite a lot of demos you can play with. So feel free when you get the slides. There's stuff like video background removal, object detection, text generation, image classification, even image generation, right? Like SD Turbo. And yeah, there's some auto stuff down here. How much time do we have? Like 5 minutes? Ah, okay. I want to show something on the phone as well, but then I'm a bit out of time. So let's just jump back to the slides. And you can try it yourself with any device, basically, you want, right? So maybe, let me quickly show you how you enable, maybe, no, I won't show you. If you have questions around that, which flags you have to use or whatever, just come to me afterwards. So just wrapping this up, the summary, right? It's difficult. There are many challenges ahead. It's not all going fine, but we're getting there, okay? So I really feel like there's good stuff that happened even just in the last months. It's quite an active field, And WebGPU is widely available now in most browsers, as I said. WebNN is getting more integrated. So there's an active working group working on that with a lot of people actually from Google, Windows, and Intel pushing. So they also want to, well, they want to sell the AI laptops, right? AI with NPUs. So they're trying to push the WebNN so people can use that. And models are getting smaller and better. And yeah, NPUs are in more devices. There is a web AI community on Discord server. It's mainly run by someone from Google called Jason Mays, but it's quite nice. So if you want to join it, feel free to hop on the Discord server. I'm there as well. It would be great to get more Europeans on so we can have more meetings at European times and not just US times, middle of the night. Yeah. And yeah, thank you. And I guess the story is to be continued. Oh, and you can connect. That's the last slide.
Thanks, Johannes. We have some time for questions.
Well, thank you very much for the presentation. My question is twofold. So one is, as far as I understand, models are produced, they are trained, and mostly everything towards the work on the browser is at inference time. So do you think, or do you envision that there will be a hardware explosion where training, like for big models, can happen on hardware, local hardware? And then, well, I just forgot the second question, sorry. Yeah, so.
Yeah, can you just repeat the last part of the question?
So most of the work that happens on local machines is inference. Yeah. So as we saw, you just like open the browser and it was this movement thing. But usually those models are trained like elsewhere, usually in the cloud. Do you think that this can happen like on locally beyond like frontier models? Thanks.
Yeah, good question. There are approaches that already did this. So with TensorFlow Lite, so you could do that like in the browser. And there's this Teachable Machine, I think it's called. It's a website where you can throw in your samples. It hasn't been done on a bigger scale, right? Because I think there are still a lot of limits, and you can fine tune or train smaller models on that. It's an interesting path, and yeah.
Okay. Just remember the second question. You mentioned like optimization algorithms for big models like quantization and other things. You mentioned like FP16 quantization. Do you think that like binary quantization can be applied into local models? And will that bring efficiency for such models?
Yeah, I think to most of it is already applied. So some of them already squeezed to the max, I would say. Yeah, so that's...
Okay, brilliant. Thank you very much.
All right.
Thanks for the talk. Awesome. One quick question. Yeah, we saw in the demo loading the models, but where actually it's stored and for how much? Because, well, if I need to download 1 gigabyte of model every time I visit the page, it may be a problem.
Yeah, that's what I meant with it, like download size and everything, right? So when you download it, it's stored in the cache of your browser. If you have many browsers like me, it's, well, different caches, which is also stupid. So yeah, the memory management is something that definitely is one of the problems because, yeah, we don't know how long it is stored. It depends on like the browser policies, and maybe they say like, oh, we need more memory, we need to free the cache, and then first they throw out the biggest thing, which probably is a model, right? And you also can't load a lot of models together in the cache because there will be some limit to it. Yeah, it's problematic, yeah.
You've shown now a couple of demos, right? The post detection. What do you think are use cases that you see for a model running in your browser rather than, aside from demos that are fun for a conference?
Yeah. Yeah, I've only shown post detection now, but I think there are a lot of also small language models these days that can run on that. So I do see some similar agentic use cases as well with the small language models, for example. Other stuff, especially on phones, because it runs surprisingly well on phones, through LiteRT actually, and you can enable like more local or more custom processing, right? So I used to work for a company where we did print products for people, so people could order photo books or whatever, and we had to apply stuff like face detection, algorithms and everything. We always had the problem of data privacy issues. If you could just run all this like directly on the device of the people, we would have had less problems with like GDPR and everything. So yeah, I think especially for that, like companies would have to think less about privacy issues. They could access the user's data without, or like process some data and get like stuff like bounding boxes out of it that is not like privacy critical. Yeah, that's some cases I see.
All right, this is time, so thank you. And we'll have a break for the lunch now.
Okay, thank you.